So again, looking at the anatomy of the wave, we were just going over that if you're for the second part of this recording, but you can also go back in the first one and look at it where we go over it there too. But you know, the phase, what I was saying is the phase is going to be constant, and from that phase being constant, or from the basic definitions of our wave number and angular frequency, we can derive the wave frequency, or the wave velocity, the propagation velocity, which will just be, as we can see in the next slide, a product of the wavelength and the frequency, where of course the wavelength is the distance, the peak-to-peak distance of the wave. Okay? So the period would be the same thing if this x were t, and we were looking at, for instance, let's draw it real quick. We're looking at y on this axis, but now t on this axis. We have a similar shape. Now we would call this time difference the period, right? That would be the time for one full revolution. So you can see it changes meaning depending on which axis you look at. But again, we're going to want to keep in mind this equation here because it will be important for our next jumping off topic, which will be the wave equation. But we then looked at some applications. We answered that question. We looked at that example, and we talked about the wave on a string, and we're able to derive this formula. And the formula I'm talking about is the wave speed on a string using Newton's laws. And that brings us to this. We just had a brief discussion about energy and power, and that brings us to one of our big results, really, of the course, is the wave equation. So this is the general partial differential equation that governs all types of wave travel. So if you're wondering if you have something, a given displacement, if it's a wave, it should satisfy this equation. Now, this is one of those cases where if you've taken differential equations, you'll note that you just have to know the solution first. So we have a solution, right? We have our wave equation, which is y of xt equals y of m, the amplitude, times the sine of kx minus omega t, right? And so from here, all we have to do is take the second order partial derivative with respect to x, which you can do. You set t equal to be constant, and then you take the same way we did with the transverse velocity, you take that second derivative, and you take the y derivative. You know, you look at both of these terms, multiply this second partial with respect to t, 1 over v squared, and you should get 0. Everything should cancel. One thing should be equal to the other. Or you should get like 1 equals 1. Something like that. Probably 1 equals 1. It's the best thing. But if you subtract them, you should also get 0. So, because they should be equal. So the way to verify that you actually have a solution to the wave equation is to just calculate the derivatives and plug them in. And that's what you can do. That's all you can do. So let's move on to the book has a weird way of deriving it. I don't usually like textbook derivations of very general theorems because they sort of make this specific case and then blow it up into overgeneralize it, where there's usually a better, more general explanation. Jagdish, yeah, what's up?
Professor, can you please return to the last slide? Just take a picture.
Yeah. Well, don't forget too, you're gonna have the this will all be recorded, so you'll be able to pause it on YouTube and everything as much as you want to your heart's content.
Okay.
So
thank you.
So keep that in mind too while we're going back and forth. No problem. So yeah, they try and define it. You can follow that argument in your book, but like I said, there's usually better, more general derivations for these things. So I have you look at those, and I want to use that to get to our next topic, which can be a little, this again, we can see sort of directly how waves interact with each other. Now you'll recall at the beginning of the lecture, I talked about how waves don't elastically collide, right? They go through each other and they'll add through superposition or interference and then go their own way. And you can see that here if you follow this, the sequence of events. You have two wavefronts sort of getting to each other. They start to combine and add to a bigger wave, but then they go through each other as if nothing ever happened. They're not affected by this collision, all right? And you'll notice that since you have two waves, you'll have two terms here, okay? And so we want these to be two separate displacements that the string would experience if each wave traveled alone, okay? So these are two independent expressions. So the displacement of the spring, or the string, when the waves overlap, is then just the algebraic sum. So this y prime is not a derivative. It's just the sum of y1 plus y2. Okay? So this summation of displacements along the string means two things. One, overlapping waves algebraically add to produce a resultant wave, not a net wave, or net wave. I was going to say not it's the same thing. Overlapping waves do not in any way alter the travel of the wave. All right. So those are two main points that we want to keep in mind as we go through this. Now, if you want to have a lot of fun with your trigonometry, for two waves that have the same amplitude, at least, we have here y1 is going to be equal to ym. Sine kx. Well, actually, they don't do y sine minus omega t, and then that will be plus ym sine kx minus omega t plus phi. Excuse me. So basically, if you yeah. Oh, thank you. Thank you. So if you want to do all sorts of fun trigonometry, thank you, that goes along with breaking these into individual terms and recombining them, you are more than welcome to. But essentially, the result after you do all that trigonometry, and of course, I think you all know I'm talking about these types of ones, sine of x plus y is equal to sine y, sine x. I think it's the sign is the same, right? So plus or sine x cosine y. It's one. I can't even remember the identity. I'd have to look it up. But you know what I'm talking about, the ones where you break it up and do the thing. So I'm not going to write it incorrectly. But those, you have to do that a bunch and do a whole lot of algebra to get this result. And again, once you put the physics here, it's just math, and the right answer is this. This is what you should get. Spending a lot of time on the algebra is not something I'm a fan of. So again, you can just use this. There's no reason to reinvent the wheel every time. But you can see that much like each of our terms, we have an amplitude term. It's a little more complicated. And we have an oscillating term. And this phi is the phase of the difference between the waves. So I want you to note something. If the two waves are identical, right? If phi is 0, cosine of 0 is 1, right? So this goes, so let me look at that. Yeah. I want to write some stuff down, so I want to get rid of this box. So if phi is 0, and that means the two waves are identical, right? So that means that this goes to 1, and this is 0, and you'll notice you just have double the wave, right? So you get the amplitude you would expect, which is the original wave just doubled in amplitude. So that's sort of a gut check that I like to do to make sure that things make sense, is that if the two waves are identical, they should just add up and give you double the amplitude, and that's exactly what happens. Does everyone see that? Any questions on that? Does that make sense to everybody? No? Sure? Okay. So, oh, geez, wow, 6 new chat messages. Okay. Okay, good. So, when we're doing that, so it behaves, but when we're looking at waves coming towards each other or looking at each other, that will be what we get. Now, I'm probably messing up a signage somewhere here because the waves will be going, so phi is just the phase difference between the waves, but I'm almost sure one of these has almost got to be plus, and I say that because the waves are traveling in 2 different directions. You'll notice if the signage is the same, then both waves mathematically have to be moving the same direction. So I'm almost sure that's going to happen, and then we'll look at the magnitude here. It'll work out to where we have the minus sign here for the omega t. Again, it really is a lot of algebra. Yeah, it's the phase difference between waves. So if one wave, I want to go back. There's a good picture of this. So you'll notice here they talk about it, but they don't really mention it. Here, these waves, for instance, they start in different places. So this little distance, this delta x, would be also, you could look at that as a change in phase, as a phase difference. So if they were the same wave, they would start at the same time, right? So here we're looking, where this picture is bad is here you're looking at the same wave. This picture is presented as one wave traveling. But I could draw the same picture, right, and say these are 2 different waves. And then the difference there would be the phase difference between the 2 waves, if you can look at it in that context. It's a nice picture. There might be one. Let me go to that. I don't want to click through all the damn slides. So let me see. It's not shifted by by 1/2 phi. You got to be careful with your fractions there. So it's and at that case, maybe it's not really clear. There should be one that's more specific. And I think we have it right here in our next slide, right? So we'll look at that. That'll be better, and we'll show it. So let's just to show you that we're starting. So we're moving on from this slide. So let's talk about that phase difference. So here we have it's a better picture, right? We have the blue wave and the purple wave, and they are in phase. So here phi equals 0, just like we did the first time. The resultant wave is that they add up to 2, right? When you add this y1 plus y2. And now here the phase difference is pi. So you'll notice that they're exactly out of phase. And you'll notice that everything, so that means when this red one peaks, the blue one troughs. And the resultant wave is actually 0, right? And then if you have some intermediate phase, you'll notice that you have some intermediate value. You just get some intermediate wave between 0 and the giant resultant wave. And you'll notice if in here, I think in this case we're looking at 2 waves. In this case, the signage will remain the same within the phase because both waves are traveling the same direction here. Okay, and we're just looking at snapshots. So when it says here that 2 identical sinusoidal waves travel along a string in the positive x direction, they interfere to give this resultant wave. And the resultant wave is what you're actually going to see, right? This is what each individual wave is made up of, how they're moving. So in this specific case, right, we very much would add, which would be different than the last time. So y prime would be equal to ym sine omega t, sine of kx minus omega t plus ym times sine x minus omega t plus phi. Okay? And when you do that, now the signs do stay the same because both waves are traveling along the string in the positive direction. They're identical and they both go the same way. So then we have to keep our signage consistent in the phase, which is, I'm talking about this sign right here. Okay? All right. So does that help with the phase questions? Does that make sense? Again, the phase is the reason why there's not a phase in this first term is it doesn't make sense for the first one to really have a phase, because you could have a phase from the origin if you really wanted to, I guess, but when you're comparing two waves, you'd have the same offset, so that would cancel anyway. So you're always looking at the phase difference between the two waves, right? In the first case, they line up, so it's 0. The phase difference between these two waves is pi, and the phase difference between these two waves is 2/3 pi. Okay? And that would come out when you're adding the amplitudes. You would plug in whatever that phi difference is here in this term. Okay? So hopefully that makes some amount of sense. Okay. So we have a little example to try this with to make sure that it can work. So what I want to do is I want to go through it, and I think we'll work on this one together. So we have two identical sinusoidal waves moving in the same direction along a stretched string, and they interfere with each other. So the amplitude of each wave is 9.8 millimeters, and the phase difference, phi, between them is 100. So we know, before we even ask what they're looking at, we've been given ym, right? And that's going to be equal to 9.8 millimeters, or 9.8 times 10 to the minus 3 meters. And the phase difference between the waves is just equal to 100 degrees. You can turn that into radians if you want, but I don't think it'll be super important here. So it wants to know, the first thing it says is, what is the amplitude of the resultant wave due to the phase interference? And is this interference constructive? Or what type is this interference, right? So it's perfectly constructive if it adds up. It's destructive if it makes it go away. So I'm guessing it'll almost certainly be constructive in some respect, but we'll see. So the first thing we have to do is we want to look up or recall, right, that our y prime m, our new magnitude, is going to be equal to 2 ym, right, times cosine 1/2 phi. So this is just a plug and chug. We plug in y into this part. We plug in the phi here. Make sure your calculator's in the right mode, and you should be able to get your new y prime. Someone give me a number for it. So I'm getting 0.13. Are you sure? 0.126, yeah, the 0.126 and 0.125 look right. So combine that together, Sean, and see if you can get the right number. Do it a little carefully. And also, when I asked what this type of interference is, I'm forgetting we're in the freshman class, which is good, because we only define, in this class, we only define constructive as perfectly constructive. That means that when the phase is 0, destructive when the phase is pi, and anything else is intermediate. So because that angle is neither 0 or pi, it's intermediate off the bat, which is fine when I ask what type of interference it is.
Professor, I have a question about this one.
Yeah.
So
Sure.
how we know the like we have to use the formula this one rather than another one?
So we want to recognize, right, that we have two. It says so we have to look at the problem, right? The problem says we have two sinusoidal identical waves.
Oh,
so the question you should ask yourself is, do I have the machinery to deal with two identical waves moving in the same direction along stretch string, right? And we just solved for that in the last. That's what we just went over. So at the risk of deleting everything, which is fine, when we look at combining waves in the same direction, if you'll recall, this is what we got.
Yes, I got it, Professor.
That's our equation. So now it asks for the magnitude, so that's just this part of it. So we go, all we need is the magnitude, and then we can plug in the numbers there and there. Okay?
Okay, thank you. I got it, Professor.
You're welcome. And then we have our two criteria, where we have constructive interference, phi equals 0, or some multiple of 2 pi. Phi is equal to pi, or some odd multiple of pi. That will get you exactly deconstructive interference, where you cancel the whole thing. And then you have intermediate, which is anything else that's not those two. All right? And because our phase for our example is 100 degrees, that puts us right into intermediate. Now, it asks what phase difference in radians and wavelengths will give the resultant wave an amplitude of 4.9 millimeters. So again, we have a displacement is equal to 2ym, right? Which hasn't changed, times cosine of 1/2 phi. Now they want you to solve for phi, and they want you to solve for phi in radians and in fractional wavelengths. In terms of wavelengths. Okay? So that shouldn't be too bad to do. You know, now you have y prime and ym, so now you just have to solve. You just have to solve for phi. And then once you have the radians, you should be able to figure out in terms of the wavelength what percentage of the wavelength goes. Because if you look at the graph, let's make some sense of that. Right? So you can look at this angularly, right? You know this is pi over 2, you know this is pi, you know that's 3 pi over 2, and you know that's pi. Similarly, this is, if we start, this is one quarter of the wavelength, this is half a wavelength, 3/4 of a wavelength, 1 full wavelength at these points, right? I'm just starting from the origin here and using the 0 to there. So you can instinctively understand, right, the unit for wavelength will be in meter, but you can instinctively see that one wavelength will be 2 pi, or right? So all you have to do is configure what, you know, when you get your radian, you can just divide it by 2 pi and get your fraction. All right? And remember, what was it? Well, that's to times pi. That'll get you into degrees. That's not what we want. We want it in wavelengths, Henry. So careful. You're just converting that 100 pi into that into radians, right? Which is fine. You can do that to evaluate it, but in order to match it, you just have to realize, again, here when you get here, this is in radians. Here you're at pi over 2, pi, 3 pi over 2, and 2 pi. When you're going through the wave, this is lambda over 4, lambda over 2, 3/4 lambda, and then lambda. You're at your wavelength, and you start again. So it's really just about meshing those two scales together and solving for your phase in terms of wavelengths and in terms of radians. All right, both of them you can describe a wave equivalently with both, or a phase equivalently with both. We'll work on that one. Phasors I'll leave you to study those on your own. I don't ask questions on them. They can make one chapter later in the course a little easier. What do you mean, what's the next step? That's it. You just do it. You solve. Yeah.
It was just changing to radians, right? 300 degrees into radians, and then you plug in the formula, right? For the displacement.
Yeah. Well, I'm gonna draw it again here. Hold on. It's not hold on. My marker's not cooperating. There we go. Why isn't it cooperating? Now I'm. Hold on. It's decided, the cursor has decided that it's going to disappear on me for whatever reason. Does the cursor even disappear? I'm going to have to figure that one out. That's obnoxious. All right. Okay, good. The cursor is back. So we have y prime now will equal 2ym times cosine of 1/2 phi. So in this case, you're given y prime. That gets plugged in here. The ym is still given in the problem. But in part B, you don't have the phase, so you have to solve for phi. So you should know how to do that from Math 200. Shouldn't need me to do that. So that's the next step, is to just solve for phi. And then once you have phi, you can interpret into wavelengths. So if you for instance, if you get phi equals pi, so say phi equals pi, right? So that would be in radians, that would be your answer. But then you could say, oh, well, it's also equal to lambda over 2.
Professor, quick
Right.
question. The y prime is the displacement, which is the phase difference?
No. So right now what we're looking at, we have the displacement, right? The displacement, this is the displacement term. The displacement term of the combined wave is equal to 2 times the amplitude of the original wave, right? That's where the ym, times cosine of 1/2 of the phase difference, phi. So you're solving for the phase difference. They aren't the same thing. All right? So this is just one equation, one unknown. You just solve for phi, right?
Yeah.
I mean, if you're having trouble seeing it, phi is equal to y prime.
No, what I'm trying to say is that the y prime means the amplitude, right?
The y prime is the, okay, I want to show you on the picture because I think it's a little easier to see there. So keep that in mind. So the y prime is this resultant amplitude here in the lower picture.
Yeah.
All right, it's added together amplitude. Okay, ym is the individual amplitude of each of these waves.
Yeah, I understand that.
And then the phase difference is this difference here between these two waves.
Okay.
See what I'm doing with it? Do you see it visually?
Yeah.
Okay, those are the three parts.
Okay.
Okay?
Yeah. So
Good.
on question B, the question we y prime it would be 4.9 millimeters, right? Because
Y prime will be 4.9 millimeters. You
before,
have to, so basically in part B, you don't know the phase anymore.
yeah,
So in part B, you have to cross this number out. You don't know that. That's
yeah.
what you're searching for. You're searching for phi, and now you have Y prime.
Oh, so okay, all right. So y prime, like I say, so y prime is the amplitude on that question, right?
Right. Y prime is, so 4.9 in part B, 4.9 is this Y prime.
Yeah. Okay.
Okay?
All right. All right. Thank you.
Got it? Again, when we figure out wavelength, right, it's just matching it sort of one for one. So when you look here, you'll have a phase difference, right? But that phase difference can be expressed in terms of radians or wavelength. So here, when the phase difference is 0, the wavelength difference is obviously 0. But look here, this is sort of the one I've been doing it. The phase difference here is pi, but you'll also notice that they're shifted, they're a half a wavelength out of phase. All right, so if you move one of these by half a wavelength, you get, this is the resultant picture. Okay, that's all that's saying, is that when you go from one to the other, it's you can either express it in terms of fractional wavelengths or between 0 and 2 pi in radians. But it's just representation. That's all. There's nothing really fundamental about it. Okie dokie. So like I said, phasors we're going to sort of skip. Again, they're used once and they're not so super great. So we're going to wrap up this chapter by going over standing waves and resonance. And so a standing wave is the interference of two identical waves that move in opposite directions. All right? So you can create something like this as the composition of one wave going one way and then the identical wave going the other way. All right? But you'll notice that as you adjust the frequency, you can get standing waves that have these two lobes, 3, 4, and you can increase the number of lobes up pretty high. It depends how much string you have, but if you have a big enough string, you can create as many lobes as you want. And this is created by those two waves reflecting. And so you'll notice we have a different displacement term here now, right? Now our magnitude term depends on x, and our oscillating term only depends on t, all right? Which makes sense because the waves are stationary for all intents and purposes. Or the resultant wave is stationary. The two other waves are traveling. If we were in class and I could get everyone to sign a waiver that no one has epilepsy, we could actually do this in class and look at the string. The problem is we have to use a pretty powerful strobe light that actually moves beyond what you can perceive. And it's really is the kind of strobe that induces seizures, though. So you really have to not have seizures. And you might discover you do have seizures, which is why they stopped really doing this. But it's a pretty impressive thing to see. That being said, they do experiments with these types of strobes at museums, and they seem to be, litigiously okay. So with the harmonics, how do we get those lobes? We call those lobes harmonics, right? In the first harmonic, which we didn't see, the length of the tube is equal to half the wavelength, all right? And the second harmonic occurs, which the one you saw with two lobes, when the length of the tube is equal to exactly a wavelength, all right? And you can sort of see this pattern forming, and you can see that the resonant frequencies in which these lobes will occur will be equal to F equals NV over 2 times L, where V is the velocity of the wave, and to the lambda is the wavelength, right? So when the length of the cavity is some integer or some integer multiple of the cavity, or 2 times the cavity rather, you get these harmonics. And of course, this starts at 2L, so that when you have 1, you get half the wavelength. Then you go up to 2, 3 halves, 4, 4 halves, 5, and so forth and so on. Okay? So that covers resonance and standing harmonics. And I think, just want to make sure that, and that is good enough for one night. That's a huge information dump. Unfortunately, most lectures are, but especially, just coming back in, getting into the swing of things. Do keep in mind, if you found that going through this lecture that you got lost, or you felt frustrated, or you didn't know what I was saying, I think if you go back and you watch it again, and remember you have that option now. This is an actual advantage to doing the class this way, and why I'm doing it this way, is you can go back and watch and rewatch and pause and see if the explanation makes sense. I recommend you guys contact each other somehow, and you'll have plenty of chances to do that during breakout sessions and things like that we'll be doing when we have our when we start our problem sets next week. And I think you should do that. It's a good thing. Oh, hold on. I have to take the attendance picture again because someone came. So I think we've got a full house, which is always good. So yeah, go back, look at it. I think the best way to do it is to try working through some of the derivations and the problems, the homework problems, which are up. So you try working on that. And again, this will be on YouTube. It won't be on YouTube till probably. So if you're wanting to rewatch it tonight, I can't really help you there. So I still have a lot of work to do getting your stuff loaded. All the lectures for the semester will probably be up by Sunday night. But these ones will take a little bit of time to get up. So and again, I'm going to stop recording because we're kind of done with that lecture part of it.